doesn't just get people drunk, it also makes DNA and RNA come out of solutions. Who'd have thunk? Okay, well, like, not that that's happening in your body, but we can get it to happen in a test tube in order to help us precipitate out and concentrate and purify DNA and RNA. And so this is how it works, as well as some of the technical aspects, such as when you use ethanol versus isopropanol, when you use which salts, temperature, all these various things. And know that the people are kind of all over the place about what they prefer, so when you hear people, you're going to get a lot of different opinions. But here's some of the science behind why different things are sometimes used, as well as basically just how it works. Okay, let's dive in. So here's the basic overview of how it's going to work. Basically, our DNA or our RNA, they have this negatively charged backbone thanks to the phosphate, and this backbone is going to make them like water like to hang out with them. And since water likes to hang out with them, they're going to be soluble, because this is basically what solubility is you have a full coat of water surrounding you. And then the water can hang out with itself as well. So you get this nice soluble mixture. And we want to get it to come out of solution. We want it to precipitate. And we want it to precipitate in this way called flocculation, where basically it all kind of clumps together and comes out, and then we can spin it in the centrifuge, and it'll come out and be this nice little pellet, which, depending on how much you have in there, could be a really, really tiny pellet or a bigger pellet. And we can use things like co-precipitants to help make the mass bigger that's going to get precipitated out. And we can use co-precipitant like GlycoBlue, which is conjugated or attached to a dye. So it's got this sugary thing, this glycogen attached to a dye, so that you can then see the pellet on the side of the tube, which is a huge lifesaver if you have a tiny little fleck. But how is this actually working? Basically, we need to neutralize that negative backbone, because that negative backbone was what was keeping it soluble. And so we can neutralize it by adding salts. And so if you have a salt, you have a neutral combination of a positively charged thing, a cation, and a negatively charged thing, an anion. And so when you stick these into a solution, they're going to dissolve and dissociate. So the positive parts are going to come apart from the negatively charged parts. So if you put in table salt, you get sodium ions, these positively charged cations, and these negatively charged chloride anions. So sodium chloride is sometimes used. We'll get more into the salts later, but also like sodium acetate, lithium chloride, ammonium acetate. And there's various reasons that we'll get into why you might want to use one of these versus another. Okay, but these salts are going to be important because they're going to provide the cation, the positively charged thing that's going to bind to and shield to the negatively charged backbone. And this is going to make the DNA or the RNA less soluble. But in order to find that backbone, we need to remove this solvent layer. So there's this big layer of water that's surrounding that backbone. And this water is going to be hiding the backbone from the salts. And so although the salts would like to hang out with, although those cations would like to hang out with that negatively charged backbone, they can't find it. And they can't find it because water is really polar. What we mean by polarity is that there's an uneven distribution of charge. And so water is neutral overall, but it has a positively charged parts, these hydrogen, and the negatively charged part, this oxygen. So basically what happens is that these hydrogens and oxygens, they are bonded together by sharing pairs of electrons. I'm not going to go into it here, but basically they're sharing unfairly, and the oxygen is more electronegative, which means it's going to be hogging more of those shared electrons. Electrons are negatively charged. This is going to make your oxygen partly negative and your hydrogens partly positive. And when you have partially positive and partially negative parts, they like to hang out with one another. And so water forms these water networks. And this is what makes water really sticky. If you stick something in water that water likes, something that's hydrophilic, then water will allow it into its network. But if the thing is hydrophobic, then water won't let it into its network. And
So when we have the DNA or the RNA with that negatively charged backbone, that's going to be very hydrophilic. So water is going to like to hang out with it. And if water likes to hang out with it, it's going to be soluble. And our goal is to make it insoluble and get it to precipitate out while keeping the things that we don't want soluble. So we want to selectively precipitate out the DNA or the RNA. And so we can do this by optimizing the salts and the alcohol concentrations, as I'll get into. But basically, why do we need that alcohol is to allow the salts to allow those cells to find the DNA and the RNA. And so right now, remember, they're hidden by the highly polar solvent, the water. What we call a highly polar solution, we say it has a high dielectric constant. So dielectric constant is going to be this measure of a solution's polarity. So how unevenly distributed is the charges, and can those charges kind of like align themselves, like polarize themselves. And so basically what happens is if you have a more polar solution, it's going to be hiding those charges better because you're going to have the solvent kind of surrounding and hiding the various cations and the various anions and making it harder for them to see each other, even if they wanted to hang out. So we can add something that's less polar, something that has a lower to lower the solution's dielectric constant. And so when we talk about polarity, oxygen and hydrogen shared unevenly, so we got a polar molecule. But carbons and hydrogen share pretty fairly, so these will give you a non-polar molecule or a part of a molecule. So if we look at water compared to, say, ethanol or isopropanol, we see we have more hydrocarbon groups. So these are going to be nonpolar parts. When you have more nonpolar parts, now our solution is going to be more hydrophobic and less polar. And so if it's less polar, it's going to hide the charges less well, and make it easier for the salts, for the cations to find the negatively charged backbone and thus neutralize it. So these are alcohol, and we'll get into more why you might want to choose one or the other in various contexts. These are going to lower that dielectric constant, decrease the shielding between the charges, and allow the DNA or the RNA to be neutralized. Once it's neutralized, now it's going to be hydrophobic. So water's not going to want to hang out with it because it's not going to offer the water anything. So it can get these partial charges from regions from other water molecules, but now it can't get that from the DNA or RNA. It can't get that charge of the DNA or RNA backbone. And so thanks to the hydrophobic effect, the water is going to basically exclude it. It's going to be kicked out of water's network, and this is going to make it insoluble. And therefore it's going to precipitate out. But now we're going to have these little flecks and precipitate and stuff throughout the tube. We probably can't even see them. And now we need to basically spin them down to get them to actually pellet out in this combined mass. And so we can stick it in the microcentrifuge. When you do this, you want to make sure that you keep the tube in you know which direction you put the tube in. So typically I stick it so that the hinge is facing up. And then I know that the pellet is going to be right down from that on the top edge of the tube. You can also mark it with the marker when it comes out so you can see it. And again, here it looks blue because I have added that co-precipitant, that GlycoBlue co-precipitant. Another co-precipitant is like LPA, linear polyacrylamide. And again, this is going to be going to kind of glob onto that DNA or RNA and help you have more mass of stuff that can precipitate out. So your pellet's going to be bigger, and you also have an easier time centrifuging it out because there's more stuff to kind of be heavier and get pulled out. Okay, so you spin it down, depending on if this is cold, you're gonna need to spin it down longer. So typically this is like half an hour or so if you've done this in the your precipitation in the freezer, as I'll talk about a little more. And then you have this little pellet, and then you want to remove the alcohol salt solution. And so you can just take your pipette. So typically I start with the bigger pipette. So like a P1000, pipette out most of it, and take a smaller pipette and get the remaining liquid, being careful not to disturb the pellet. And the GlycoBlue is going to be really helpful because this pellet could be really hard to see, especially if you've used isopropanol instead of ethanol. Then your pellet is going to be clearer and stuff. But anyway, you pipette that out, and now you're going to do a wash with 70 to 80% ethanol. And typically this is like cold ethanol. The point of this is to remove any excess salt. So right now you've precipitated out, and so you had some salt helping you out, precipitate out the DNA or the RNA, and now you want to get rid of that excess salt. Your DNA or your RNA is still going to stay dissolved or stay insoluble, because basically now you have this big clump of stuff, and it's going to be harder to resolubilize. So this excess salt is going to be soluble in this ethanol solution. Even your RNA or your DNA is going to remain pelleted. So typically you add the ethanol, and then you kind of dislodge the pellet from the wall, being careful though not to lose the pellet in your centrifuge or in your pipette or that sort of thing. Then you spin it again. Thankfully this time it's only for like 10 minutes, and then you pipette that out. So we say you like aspirate off the liquid. Depending on who you ask, you might get different advice about this next step, but typically what I do is I just air dry. So I take a pipette and I suck out the liquid, and I take a smaller pipette and I pipette out the little liquid. Try not to like splash things around your tube, because then you're going to have stuff on the wall it's going to be harder to get rid of. Also, when you take your tube out of the centrifuge, be really careful you're not like disturbing or dislodging things. Just be really careful. It's helpful if you like take your pipette over to the microcentrifuge instead of taking your tube back to your bench in order to aspirate off that liquid. So try to pipette out as much as you can, and then you can air dry it to evaporate any lingering ethanol. Some people say like to use a speed vac to help with the air drying, and then other people like, don't use a speed vac. I've never used a speed vac. I always just air dry it. But you want to get rid of the ethanol that can interfere with downstream things. Once it's dry, but not over dry. So if you over dry it, then it will be harder to dissolve. And so when you dissolve it, we can also have this like resolubilization. So basically now you want to add a liquid that the DNA or the RNA is soluble in. So this could be water, this could be some sort of buffer, but something that now your DNA or your RNA would be happy to hang out with, especially now that you've removed that excess salt. And now when you redissolve it, it's going to be soluble by itself. You might need to heat this up a little. So like, I think people say like 50 or so degrees Celsius for DNA, like 40 for RNA. Sometimes this can be an issue if you're having difficulty with the resolubilizing it. Also, you might need to do more washes if you do ethanol or isopropanol in your initial step, because isopropanol is going to be better at precipitating the salts that you didn't want precipitated. So you're going to have to do more ethanol washes in order to make sure you remove all of them, especially if you did your isopropanol in the cold. So let's get more into this idea of ethanol versus isopropanol. So my biggest advice is to like look at the protocol for what your uses are, because this can often give you good information. But here's kind of the basics about why sometimes you might want to use ethanol and sometimes you want to use isopropanol. And so what is the difference? Well, structurally, isopropanol has this extra CH group, and so it's going to be more nonpolar. It's going to have a lower dielectric constant. If it has a lower dielectric constant, that's going to make it have less shielding of those charges, make it easier for your cations to find the backbone, and thus it's going to neutralize it better. And so it's going to have more precipitating power. So basically you don't have to add as much isopropanol to get the same amount of like precipitation power. So if you don't need to add as much of it, then you can fit more. And if tube space is an issue, this can be good. So this can be good if you have doing like a large scale preparation or something and you have a lot of volume. The isopropanol, since you don't have to add as much, now you might be able to fit it all in your tube. Also, a consequence of that higher precipitating power is that you can more easily precipitate lower concentrations of nucleic acids. And then again, especially if you have a co-precipitant like your glycogen. It's also good for precipitating bigger things, so bigger pieces of DNA and stuff, whereas with if you have smaller things, you might want to use ethanol. Also, because of that precipitating power, you don't need to, you can do it at room temperature. So depending on who you ask as well, you can do the ethanol at room temperature or just on ice. Some people recommend you do it at -20. Other people recommend you do it at -80. And also the time of the incubation can vary. If you have like small nucleic acids, if you have like small RNAs and stuff, you might want to do it longer. So typically I do at like -80 for at least a couple hours or overnight, or at least -20 in some cases. But basically, I don't know how important that is. It depends on who you ask. It depends on where you look. You'll get very different advice, but there's someone directed me to this paper I'll link to, where basically they show that it totally depends on the nucleic acid that you're trying to precipitate, and that you can vary all these different conditions, and you can, they're all going to vary. So salts, temperature, and ethanol, isopropanol, all these various factors, it's going to be very dependent on what the sequence is, what the size is, whether or not it works better or worse. One thing though about doing it in the cold is that then it's going to be more viscous, so you're going to have to centrifuge it longer or let it thaw to room temperature first. You don't want to use isopropanol though in the freezer. When you cool isopropanol, because it already has that better precipitating power, you have more risk of precipitating things you don't want. So with the isopropanol, even when it's not cooled, it's still going to have more risk of precipitating out a bunch of salts. And so this is why it's really important when you're doing this ethanol wash step, that if you did the isopropanol, especially if you had a lot of salt in your solution, and or if you did the isopropanol chilled, you're going to want to do multiple ethanol washes. Okay, isopropanol is also less volatile, so it's harder to evaporate. But since you're removing it and then doing these ethanol washes, this is less of an issue. Okay, so that was the ethanol versus isopropanol. Then which salt? So basically this kind of like standard is sodium acetate, often at the pH of like 5.2 and 0.3 molar final. So this is good for routine precipitation, but it's bad for samples with lots of protein because those proteins will precipitate out. If you had, speaking of protein, remember SDS from SDS page. SDS is this detergent that we often use to solubilize proteins when we are doing SDS page. So basically this gel where we denature the proteins, keep them soluble with this detergent, and give them this negative charge with this detergent that can help them go through the gel. SDS is going to be soluble better in this sodium chloride solution. So this is going to keep it from precipitating out. Another common one you'll see, especially with RNA, is lithium chloride. So this is good for RNA because for a couple reasons, RNA needs more ethanol. So if we go back to the volumes that you need, for isopropanol, you're typically adding like 0.7 to 1 volumes of isopropanol per reaction, low side for DNA, higher side for RNA, and for the ethanol, 2 to 2.5. Again, lower side for DNA and higher side for RNA. So it's about 2 for your DNA and about 2.5 to 3 for your RNA solutions. And this comes down to RNA being more soluble because it has that, it has this 2' OH group that makes it more polar and makes water want to hang out with it more. So lithium chloride, though, because you're adding more ethanol, now you have more potential for salts to be precipitating out, but lithium is going to be more soluble than the sodium acetate and stuff. So this is going to keep it soluble, but the chloride ions can mess up things like in vitro translation. So basically when you're trying to make proteins in like a test tube, and this often you make these RNA templates for it, and then you purify out these RNA templates for it. And you don't want to use lithium chloride when you do that, because then those chloride ions will mess things up. Another thing where the salt you choose can mess up future things is ammonium acetate. So ammonium acetate is good for removing DNTPs. So if you did some sort of sequencing reaction, if you did some sort of labeling reaction, these DNTPs, so these like free nucleotides, will stay soluble in the solution. But you don't want to do this before you do some sort of labeling, because with T4 polynucleotide kinase, the ammonium ions are going to inhibit this kinase, to mess up your labeling. Another place where things can mess up future steps is your co-precipitant. So people used to use like tRNA, yeast tRNA, to help. It's a nice cheap source of some tRNAs that can help you precipitate out your thing. But people switched to using glycogen and LPA, because when you have tRNA, you're adding extra nucleic acids, and then this is going to mess up your 280 or your 260 absorbance when you go to measure with the nano drop, because now you have something else that's going to be absorbing. Okay, so hope that helps, and happy precipitating.